right, I'm happy to be here today and excited to share this work with you. So today I'm going to talk about some work that we've been doing. I work with all vegetable and berry crops in New Hampshire because, well, that's how we do things. And a lot of my work is focused on extending the growing season and work in high tunnels. And today I want to talk a little bit about a project we've been doing working on nutrient management in high tunnels. And it's actually part of a bigger project focused on both nutrient management and integrated pest management in tunnel systems. And we have a great team from UNH, where I am, and the rest of northern New England. We have some folks from University of Maine, the Maine Organic Farmers and Gardeners Association, University of Vermont, and we have some assistants from folks nearby here at Penn State, and also Carol at IPM Labs, who you just heard from. So we have this project. And I'm only going to talk about a piece of it today. I'm going to talk about the fertility piece, not the IPM piece. And our main objectives were to really fill some knowledge gaps that our growers in northern New England are facing. And what I'm going to share is describe what those knowledge gaps are, and then kind of talk a little bit about what we learned. So a little background, it's important to sort of set the stage because I suspect there's a real variety in production systems represented here. Whoops, how did that do that? So what I'm talking about and what our research focuses on is really in-ground production. In our region, it's a split half and half, I would say. Many high tunnel growers grow in containers of various sorts and fertigate all of the nutrient requirements, but many of them grow in ground, like you can see here. Most grow indeterminate varieties. There's a little bit of determinate variety production in tunnels, but most of it is indeterminate. And I should say we're focused on tomato because it's the most common thing our growers grow in tunnels. Our research is focused on organic sources of fertility, and there's a reason for that. We work with both conventional and organic growers, but most of our conventional growers use a fair amount of organic amendments pre-plant because they like what it does in terms of long-term slow release of nutrients, and they feel they're getting an improved soil health out of those slower release products. So that's why we chose to focus on that. And we are really looking at as a long production season in the tunnel, or long for us in northern New England. So this is one of my colleagues and collaborators on the project slide. I borrowed it shamelessly. Bruce runs the soils lab at the University of Maine. And he likes to use this analogy of high tunnels as being really different than our typical field production systems because they're essentially irrigated deserts. They are completely excluding rainfall, although as we know from some of our work, the rain does penetrate sideways and infiltrate a little bit. But by and large, we are creating this artificial environment, and as a result, we think that fertility management in tunnels is really different than in the field. We see all kinds of water movement up. We see it through the plants actually transpiring, but also evaporation during the summer months. And we don't necessarily see the typical leaching that we get in outdoor field production. So what we have is upwards migration of certain nutrients, and we just have a different kind of a management situation. So this is what we see when we do work visiting growers in the region. We see a bunch of problems pretty consistently with high tunnel nutrient management. And again, we're focused on tomatoes. So we see some of those nutrient-related disorders that you guys have already heard about earlier in the session, yellow shoulder, uneven ripening. We see a lot of that. We see also this situation when you use a lot of organic pre-plant fertilizers, you see a fair amount of excessive vegetative growth early in the season, really vigorous plants that then when they get a good fruit load on them, we tend to see that sets them back and we have weaker growth later in the season. And some growers are fertigating to make that up, but certainly the organic growers are often not. So we see this problem where we have kind of a misbalance between application and availability and needs of the plant. So we also see that if we look at all the soil tests that come into our states, which we do because we run the labs to see that, we see that soil nutrient levels appear deficient according to our field soil standards pretty commonly, even in high tunnel tests. We sometimes see them off the charts excessive, but we see, for example, potassium deficient pretty much constantly. And we also see long-term buildup of soluble salts in high tunnels. In addition to those things we observe, we also frequently field grower questions, and the big questions that we're getting a lot of now are which soil testing methods to use. I don't know does anybody here use saturated media extract in high tunnels? Okay, no. Some of our growers are so saturated media extract is the way you would test what's immediately available for uptake by the plant. It's commonly used by greenhouse growers in transplant production. And some of our growers are using that in conjunction with field soil tests because they feel it's getting us, giving a better picture of what's immediately available for uptake. But this work has not really been calibrated for Northeast tunnel production, and so they're using it, but we don't really have great recommendations to go based on. What nutrient guidelines to follow? All of the soil tests and our nutrient recommendations are calibrated for for field production. What should we be doing in high tunnels? And we suspect it's really different. And how do we respond to those deficiencies mid-season? So we started trying to fill some of these gaps and really just take the opportunity to learn more about high tunnel production systems by really focusing in on just one thing and thinking, all right, we thought if we focused on potassium and trying to really calibrate high tunnel soil tests for potassium and look at yield and quality responses to this range of potassium rates, we would be able to actually try to refine and focus on and give good recommendations for how much K is actually needed. And so our justification for that really was that there was tons of potassium deficiency in tunnels, and about half of them were, the tunnels routinely tested are measuring below optimum. So we had 3 different sites, and in these sites we established all these fertility treatments. We held nitrogen constant, and we varied K from rates of 0 to 900 pounds to acre, and all these sites were reading pretty low in K when we started. And I'll try to skim over those details. We used OMRI-approved nutrient sources. We used blood and soy to provide the N, and potassium sulfate because we figured that would be relatively soluble and available quickly for the K. So, it really does jump ahead like crazy. Just one of the reasons that we thought this was really important work to do was because we thought that we were lowballing our potassium requirements in high tunnels, especially for these long-producing indeterminate varieties. So our common spacing is about 6 square feet per plant. We might have 4 feet between rows and then 18 inches between plants within a row. And at that spacing, if you get 5 pounds of fruit per plant, that corresponds to about 19 tons to the acre. And our tomato field soil tests are calibrated for about 20 tons to the acre yield. And for our growers, 5 pounds per plant for those indeterminate plants is really low. It is very common to be up in the 15 or even up to 25 pounds to the acre or more in some cases. And so if you look at those yields, we hypothesize that you might actually be needing up to 4 times as much potassium as we're recommending to really support those high yields. And what we're recommending typically for a low K situation is about 250 pounds to the acre. So we figured we were probably lowballing it. So this is just a layout of our sites, and I want to kind of orient you. This is I'm here in Durham in southeastern New Hampshire, and so that's one of our sites. We have another site up in northwestern New Hampshire and another site in Maine, and the red dots are our collaborators, but the green dots are where we did this work. We had different tunnel configurations in the 3 sites, but in all sites it was a replicated trial. You don't need to know the details of how we replicated that. And so because, the abbreviation was short, I meant to say I'm a plant breeder by training. I don't know anything about soil fertility. So this was a good experience for me to dig into this. And what I thought we were going to get was this. So when you do soil test calibrations, what you do is you rate all these levels of soil K from low to high, and then you measure yield and quality and all these other things, and you get a beautiful line like that, and you can say, all right, this is the amount of soil K we need to guarantee nice yields. Do you guys think that's what we got? It's not what we got. It's not what we got. I'll tell you what we did learn. So one of the things we learned was that you lose K really quickly in high tunnel situations. So this is one of our sites. This is the one in northern New Hampshire. And just for perspective, this little green bar is what we consider to be the optimum range for potassium. And at the start of pre-plant in the first year, we started with applying 750 pounds the acre of K. Oh, I have those colors backwards. Yeah, I just noticed that now. So 750 is actually up here, 450 is in the middle, and then 0 down here. And so we started with a nice range. By the end of that growing season, we had sucked out an enormous amount of K. We'd gotten below optimum already in that low treatment. And then over winter, we lost even more, a lot more. This is a covered tunnel where there's no rainfall, but there's clearly some leaching and lateral movement. So that was one thing that we learned. And then we didn't apply any of that second year, and you can see we were well below K very quickly, below optimum. So one of the side things that we learned in this project that we did not set out to do is we started wondering about soil testing and sampling methods in tunnels. So mostly when you take a soil sample, you take a nice distributed, sample from, rooting zone depth from all kinds of areas and mix it together. Well, when you're in a high tunnel over the winter and you go to take your soil test in the spring, you often notice all of this salt residue on the surface. So we did a bunch of, in a few sites, we did a bunch of sequential sampling where we took like the top inch, the next inch, the next inch, the next inch, and analyze them separately. And what you can see here is that once you get sort of deep in the bed, our soluble salts levels are at a nice low-ish level. But in that top inch, it's way high. We would be very alarmed to see salt levels that high. We would say, well, you'll have a hard time germinating crops, for example. And so the take-home message here is that distribution of your samples is really important, and you have to be careful to not just scoop samples off the top and think you're getting any kind of reliable indication of what's actually in the soil. And when you go and you analyze, this is actually a different site. If you analyze all the different macronutrients separately, you see exactly the same thing. Those top inches contain all kinds of nutrients, and when you get down to 2 inches and deeper, there's not much there. So so we're very used to, in our work with growers, talking about this concern about long-term buildup of soil, of salts by repeated excessive fertilization to meet crop needs. And we talk about how you uncover the poly, take the poly off when you swap, and try to get the rainfall to leach those nutrients out. We talk about overhead irrigation to leach those nutrients out periodically, diluting the salts in various ways. But we had never really talked about this short-term stratification, which happens in just a winter. So it's really, really important to sample the entire rooting depth of the bed is what we've come down to on that. Logical, but not something we'd necessarily thought about. So that was our first couple of years. We were playing around, and what we saw was that we really did a good job of depleting the K, but we didn't see really strong relationships between the K rate and yield. So in our current project, we figured we needed more time to see those relationships. And so we basically continued that experiment and reestablished those potassium gradients. We also switched nutrient sources. It turns out that, well, it's a long story why we switched, but we're now using nitrogen, we're using a Nature Safe 1300, still using potassium sulfate. And we thought we could get that great response to K. Hang on a second here. So here is kind of the layout of what we did and what we saw. These are potassium levels measured over time. These time points, this is one of our sites. This is at our research farm in Durham. So this is mid-growing season, so at first harvest in 2015. This is the last harvest at 2015. This is pre-plant in 2016. Then we applied some more fertilizer, more K. Then mid-16, late 16, early 17, mid-17. And again, for reference, the optimum range. So what you can see here is, again, that same thing we saw in that North Haverhill site. We saw it across all the sites, where in this treatment here, I just am showing a subset of the treatments to kind of simplify the graph. These are the amounts of K2O added. So here's 750 pounds to the acre that first season. By the next season's planting time, we had fallen back into optimum range. We added another 600 pounds to the acre. And by the beginning of the next season, we were again below optimum. So this was enlightening to us because we've applied 1,350 pounds to the acre of K over 2 growing seasons, and we're back into the low level. So if you don't apply any, yeah, you stay low. I guess that wasn't revolutionary. But so again, you can see that you lose it both during the cropping season and during the winter. This is in our main site. Same kind of setup here, same kind of deal. In this case, we had slightly different soil types in all sites. Theirs was actually not as heavy as ours. Ours is not a heavy soil. Theirs is a little lighter yet. And what we saw there was that we pretty much had a very hard time getting ourselves to stay in the optimum range, even for that crop. And so we were pretty much perennially below the levels that we should be to get that crop what it needed. So this was all surprising and not really what we expected. We expected we'd really be accumulating high levels in those highest treatments. We did see symptoms of potassium deficiency. This one on the right is a really good illustration here. So this is on the new growth. This was in our lowest K treatment. You can see this kind of marginal necrosis around the edges of the leaves. Looks kind of like a tip burn sort of a phenomenon. That's classic. This leaf on the left is actually showing some magnesium deficiency probably as well as potassium deficiency, but the potassium thing is really, you can sort of see a marginal burning here. So, so we did see that, which was, you know, nice to see. It meant we really were having some deficiency. We saw this tremendous range in yellow shoulder. We were using a single variety that's really susceptible to yellow shouldering. And so we saw, you know, we were able to rate the fruit in terms of severity and incidence of yellow shoulder, as well as marketable yields and so forth. And so there was a lot of variability that we thought we could correlate with K level. And so what we found was that in some cases we really could see somewhat a relationship. Not as tight as that nice little curve I wanted there to be, but I'm learning that soil fertility work is not like that. And so what we've got here, this is marketable weight over here on the left, so marketable fruit weight, and this is soil K measured at the first harvest. And so what you can kind of see is there is sort of a relationship. When you get into these higher levels of soil K, we have consistently higher marketable weight than when you're down at these lower levels. So that was encouraging. This is Durham. I'm just showing you a little bit of the data because it's too complicated to look at all reams of it. So this is in our main site. This is soil K measured at the last harvest, so it had really depleted already. And this is frequency of yellow shoulder in the fruit. And this was a really nice relationship because you could see that there was a way higher frequency of yellow shoulder at those very deficient levels of K. And, you know, it did go down at those higher levels, so that was exciting. And we also saw this is soil K at last harvest, again still in Maine, and this is foliar K, so K measured in the leaves at that last harvest. Now at that time you would expect that most of the K has been actually removed from the leaves and put into the fruit, which is what happens when you have a big fruit load and they ripen. So you would expect to have it them be pretty low levels, which is actually what we see here. But you see this relationship, which is really exciting. So we can start to say, all right, so we need to be high. We need to get higher soil K levels is what we need in order to really pinpoint those levels. What are the right levels? But sometimes we saw this. So this is actually foliar K in Durham compared with soil measured K at the last harvest. And there is, I'm hard pressed to see a relationship. And I can't really explain that except to say that there's a lot of noise in these data, and it's a lot harder to do this work than to do this and get really nice tight relationships like I was hoping for. So there's a lot left to figure out. One of the things that we started doing when we were looking through the data and found these things that were just not quite lining up the way we thought we should is Bruce, who runs all of the soil samples in his lab, went and looked at the soil samples. So this is a little box that we keep the soil samples in, and that's one of the archived samples from last year that he went to go look at. And he said, well, isn't that strange? What are all these particles on the top? Well, he said, can you send me some of the potassium sulfate that you guys used? And I did, and this is the potassium sulfate we used that we bought from a local supplier of organic potassium sulfate. And it turns out that those particles are really quite large. I don't have anything there for scale, but they're several millimeters across, and those particles were still present after the full growing season and irrigation with 2 lines of drip and so forth straight through the growing season. And we managed to get a bunch of other different brands of potassium sulfate, and we got one from another supplier, and it looked like this. So much more soluble, much more rapidly dissolved. And what we are finding is that through lack of specifying or knowledge that there was a difference in granular sizes, that actually we weren't getting complete release of all the K that we put on, which is a factor if you're using some of these mineral sources that should be dissolved pretty quickly, but maybe don't necessarily in this kind of case. So what we determined was happening was that we were getting a fair amount of incomplete release of fertilizer, and we attributed that to the fact that there were actually dry zones in the beds, even though we were trying our best to irrigate with a tensiometer, meeting the nutrient, the water needs of the crop. We don't necessarily have complete dissolving of the water-soluble fertilizers like potassium sulfate. Our organic nitrogen sources were not fully dissolving. We would see those particles merge up to the top. And what that means practically is that a portion of those applied nutrients are there, but they're never really getting to the plants. So in terms of recommendations, what we're taking away from that is that we need to use as fine a granulated formulation as we can get a hold of. We need to increase the number of lines of drip in each bed to be able to make sure that soil stays moist, and that when you are actually, before planting, you should make sure that that entire bed is thoroughly moist, which might not always happen in a high tunnel situation. And so Bruce is suggesting that we should saturate the entire soil volume a few times during the season if possible, which is often not done in a tunnel setting. So even though we talk a lot about meeting the tomato water needs, and we spend a fair amount of time trying to do that correctly with tensiometers to avoid all these other problems associated with drought stress, we now think maybe that's going to be a pretty big factor when you're looking at these slower release nutrients that need water to become available to the crop. Just a word about yellow shoulder. So we talked a little bit about that earlier in the session. There are other ways to manage yellow shoulder, and the message that we took home from this was that high K helps, but it's certainly not the whole thing. The other thing is to avoid sun scald and excess light exposure to the top of the fruit, and to avoid some of those non-uniform green varieties. Like this one is Big Beef. This one is, so these are two tomatoes. This one has the uniform green trait, so it doesn't have those green shoulders when it's immature. And that one will be much less likely to experience those ripening disorders as ones that have that green shoulder phenomenon. So there's other ways that we have to work on reducing those problems in the tunnels besides just potassium management. Whoops. So to wrap up, what we've learned from this work so far, I think we feel pretty confident in saying that high tunnel tomatoes are luxury consumers of potassium in tunnels, and that the K levels that we measure in the fall are a lot higher often than the ones we measure the next spring. So that has implications for soil testing and when you do the testing to determine your nutrient application rates for the next season. So it kind of suggests you should do it closer to spring if you can. Also, that K alone is insufficient to reduce yellow shoulder problems, and that your strategies for actually taking the sample for soil in tunnel require some more thought and maybe a different approach sometimes than you might have been doing, or more attention, I should say. Also, that water management is critical, not just for the plant, but also for nutrient management. And that we know that decisions about when to apply fertility are really important for those that are doing these pre-plant applications, but we don't have really clear conclusions at this point. So they're not obvious to us exactly what the recommendations should be yet. And that's where we're continuing to do more work. And my last conclusion is that working with nutrients and fertility is much more complex than I thought it was going to be, and it's slower to get solid, definitive answers than I thought it was going to be, which maybe falls under the more I learn, the more I realize I don't know category. But I'll finish with a photo of my collaborators in this project who are all working with us on the nutrient management and the IPM piece. And of course, they're very important to the success of the project. And I would be happy to answer questions that you have, and we'll see if I can answer them. Yeah?
Can you put too much potassium on? I mean, what if you put 2,000 pounds on?
Well, so the question is, can you put on too much potassium? And from an environmental standpoint, the answer is yes. From the crop standpoint, we thought that the answer was yes and that you could get some burning and some adverse effects. We have not seen that. Mind you, we're using potassium sulfate, and I think part of the problem is that some of it is essentially staying as inert particles and not releasing. I think the answer might be quite different, and the answer is probably yes, if you're using something like potassium chloride and you're putting it through the drip and it's like immediately available. So I think the answer is probably yes, but I haven't seen it in our work.
So you say that the potassium level actually decreased over the winter. Where did it go?
It's a good question. So there's lots of possibilities there. I don't think it evaporated. I don't think it evaporated. In a tunnel, you don't have water coming down. But often, unless you're on a super flat site with the tunnel way raised up, often there's a little native slope to the land. And we think that in the sites where we measured in all of our sites, nothing's level. And so we think there's probably some underwater movement and some loss that way. So that's one possibility. The other possibility is that when you have this problem with the soil, with the particles not fully releasing, your tests are affected if you get a particle sometimes and not another time. So that shouldn't have affected because, well, it was consistent across all sites, but I think it was probably leaching. But I don't have really great evidence that it was, I don't know that for sure. Yeah.
My understanding about typical soil testing methods is that the result that you see on that test, for instance, like there with Penn State, indicates the amount of potentially usable amount of, in this case, potassium, which is only a very, very, very small fraction of the actual amount of potassium in the soil. So couldn't it simply make sense that without winter moisture in the tunnel, there's no biological activity, so there's no available potassium? In other words, if you watered the high tunnel, because every year my spring soil tests always show a much higher level of potassium in the field than my fall soil tests have. So it seems to me like could that be a possibility that biological activity would make that potassium available, but that's not happening in this desert environment?
Yeah, so in theory, I think that maybe could be happening. With potassium, the soil test method should be actually accessing, with potassium specifically, it should be accessing everything that is everything that is there. And most of it should be available to the crop, unless it's tied up in soil particles where you aren't going to get it really either way. So I think it should mimic pretty closely what is available to the crop, and it shouldn't have to do with potassium, like it's not mineralized, like nitrogen is out of organic matter. So I wouldn't have thought that would be the reason for it. But to be honest with you, we don't know exactly what the reason is. So I'll say anything's possible. How's that? Yes?
In your early slide, you showed that white precipitate on this. What is probably precipitate?
Well, it's nutrient salts, but it may not be just like sodium chloride, for example. When we test that, it's got sodium in it. It's got it probably is some sodium chloride, but it's also probably other mineral salts precipitating out too, many of which are plant available nutrients. So if you could just get it incorporated and mixed, that would be the solution. But we didn't test to see exactly what the white is. Yeah.
It tastes bitter.
Yeah, right. It smells good. No, I'm just kidding.
Yeah, but if I want to get that incorporated and mixed in the wintertime, what I'll do is I'll just turn my overhead sprinklers on and leave them on for 24 hours. Well, am I just bleaching away all my potassium?
Probably, no. Yeah, so salt buildup is both a good and bad thing because salts are nutrient salts. And, so, you know, yes, you are leaching the nutrients, but you are also leaching non-nutrient salts as well. Yeah, it's trade-offs. Yeah.
What about the salt accumulation is a problem if it's in the top 2 inches or so? What about deep tilling?
Yeah.
To try to alleviate the salt problem, plus also get more nutrients in the root zone. Is this the recommended procedure?
Yeah, I don't even think you need to deep till per se. You know, some growers do till in their tunnels, but some really don't have the capacity to till and really just mixing. So, you know, broad forking, anything to get it a little bit distributed is probably the answer. And on the surface is not really a problem for plants that you're putting in as transplants and so forth. It's just that you won't get an accurate measurement if you're trying to measure soil, do soil testing. You have to know that it's way higher on the top than in the bottom. Yeah, so I don't even think you need deep tillage is my answer. Thank you very much.